Bismillahirrahmanirrahim. I am Mrs. Nadia Rao from Abhibarn All Girls College, Ahmedabad, and today we are starting with lecture number 4 of chapter 16, that is hydrocarbons. In today's lecture, we are going to discuss relative stability of alkenes, structure of alkenes. We are going to discuss few methods for preparation of alkenes, that is dehydration of alcohol and by dehydrohalogenation of alkyl halides. And we will be discussing about reactivity of alkenes, reactions of alkenes. In reactions, we are going to discuss only two of the reactions in today's lecture, that is hydrogenation and hydrohalogenation. Let's move on towards some questions from the previous lecture that I have asked you to do at your homes. Let's discuss them. First one was from the activity. You had to name these olefins using IUPAC nomenclature. The answer of first part, A part, is ethene. Answer of second part, as you can see, this is a simple propene. You don't need to write one propene. When there is nothing written with the name, it means it is understood that double bond will be at position number 1. Next one is 3-hexene. You can see there is numbering can be started from this point 1, 2 and 3. This is third carbon atom. So we can call it 3-hexene, or otherwise you can write it, both of the writing forms will be correct. You can write it as hex-3-ene as well. Hex stands for 6 carbon, 3 for the position of double bond, and ene stands for double bond. The next compound is this one, and name of the compound is 2-methyl-propene. Answer of part E will be 1,3-pentadiene. Let's start numbering from this point 1, 2, 3, 4 and 5. So we can see at position number 1 and position number 3 there are two double bonds. So it will be a diene. We can write it as 1,3-pentadiene, or other way of writing the name is penta-1,3-diene. The name of the last part is 1,2,3-hexatriene. You can see it is a 6 carbon compound in which there are 3 triple double bonds present, which are at position number 1, 2 and 3. So we can call it hexatriene, and we have to mention the number of position of double bonds, that is 1, 2 and 3. You can also call it hexa 1,2,3-triene. Hexa stands for 6 carbon, 1, 2, 3 for the position of 3 bonds, triene stands for 3 double bonds. The name of G part from the same question will be 2,3-dimethyl-2-butene. Because you can see there are two attachments, these are methyl groups, and they are attached at position number 2 and 3. We can number it from either side. In both of the cases, attachments will be getting number 2 and 3, and it is 2-butene because at position number 2 there is present a double bond. You can also write the same name in this way, that is 2,3-dimethyl-bute-2-ene. Now buta will not be utilized. The term buta will be utilized when there will be diene or triene in that case. The next part is H, in which you can see there are 4 attachments, that is 4 methyl groups are present, which are present at position number 2 and position number 5 of a hexene. In this hexene, there are 6 carbon atoms. At position number 3, there is a double bond present. So the name of the compound will be 2,2,5,5-tetramethyl. There are 4 methyl groups attached, 3-hexene. You can also write it in this way, 2,2,5,5-tetramethyl hex-3-ene. Now hexa will not be utilized. It would be hex-3-ene. But if there is a 2 double bond or there are 3 double bonds, in that case you are going to use the term hexadiene or hexatriene. Question number 2 was to name first 2 parts according to IUPAC system. So the name of first part will be, you can see this is a butane again, which is having 2 double bonds. So it will be a butadiene. At position number 1 and 2 there are double bonds, 2 double bonds, and at position number 3 there is a methyl group attached. So we are going to number it from this side. The name of compound will be 3-methyl-1,2-butadiene. We can also write the same name in this way, 3-methyl-buta-1,2-diene. Now you can see the term Here we were not using the term buta, but was used, and now buta will be utilized when there are 2 or 3 double bonds. The name of part B will be, you can see again there are 2 double bonds which are isolated from each other, which are away from each other. We can call this compound as 2-ethyl 1,3-butadiene. This is ethyl group present at position number 2, and at position number 1 and 3 there are 2 double bonds. We can also write the same name in this way, 2-ethyl buta 1,3-diene. The next 2 parts we have to name them according to their trivial or common names. But there is something wrong with these structures. As you can see, trivial names are those names which are not utilized now. They were used before IUPAC. In this compound, there is something wrong with the numbering that they have shown. So, no trivial name can be given to this compound. That's why I'm skipping this. Because the alpha position mentioned over here, this is not the correct alpha position. If this is alpha, we cannot name the rest of the compound. In case D, you can see, again, there is something wrong with the numbering that they have shown. Do remember, girls, whenever there is any functional group present, the carbon which is attached next to the functional group is usually called alpha carbon. And carbon adjacent to alpha carbon is called beta carbon, and carbon adjacent to beta carbon is called gamma carbon. But right now, this is the double bond which can be considered functional group right now. So if this carbon is holding a double bond, this one should be the alpha carbon, this should be beta, and this should be gamma. But they have named it gamma carbon. So anyways, we can name it as gamma heptene. At position gamma, there is a double bond present. So this is what can be done right now. The third part is you have to name it according to the derived name. That is the name which has been derived from the either common names or from the IUPAC system. In this compound, we can see this is a vinyl group present. Vinyl group is CH2 double bond CH, and this is a methyl group which is present. So let's name this one as the parent compound. This would be methane, and along with methane, there is attached a vinyl group, so it would be called vinyl methane. Otherwise, it is simply propylene or propene in accordance with the IUPAC nomenclature. The third part of same question was, you had to draw geometrical formulas of the following compounds, structural formulas, and you had to show the geometric isomerism in each case as well. I'm going to show you structural formulas right now. Geometric isomerism we will be discussing later on in the next few lectures, and then you would be able to understand and draw their geometric isomers as well. So right now we are discussing only their structural formulas. First one was 1,3-butadiene. This is structure of 1,3-butadiene. This is the structure of 1,3-butadiene. This is a butene which is holding 2 double bonds at position number 1 and 3. This is quite a detailed structure, so I think there is nothing that can be explained. The next part is 1,2-pentadiene. The structure of 1,2-pentadiene is shown over here. There are 3, 4, and 5 carbon atoms. You can see 1, 2, 3, 4, and 5 carbon atoms. At position number 1 and at position number 2, there are 2 double bonds. Rest, you can draw this carbon and last 2 carbon in the straight chain as well. This is the representation. You can represent it in any possible way. These are 2 just hydrogens which are attached. Third part was 2-methyl 1,3-butadiene. The structure of 2-methyl 1,3-butadiene can be drawn in this way. We are going to number it from this side. That is, this is first carbon atom, then comes second, third, and fourth carbon atom. You can see this is carbon 1, 2, 3, and carbon number 4. So at position number 2, there is a methyl group and there are 2 double bonds. So this can be the possible structure for 2-methyl 1,2-butadiene. C part is 2,4-hexadiene. The structure of 2,4-hexadiene is drawn over here. You can draw the structural formula as well. 1, 2, 3, 4, 5, and 6 carbon atoms which are holding at position number 2, and at position number 4 there are 2 double bonds. The last part is 3-methyl 1,3-pentadiene. we have to number it from this side. This is carbon 1, 2, 3, 4 and 5. At position number 1 and position number 3 there are 2 double bonds and there is a methyl group at position number 3. Another activity which was given to you was from the portion of alkynes. Answers are being told to you people right now. The first part was this one, in which you had to give IUPAC names to the compounds. This one is simply butane. You don't need to write 1. There is a triple bond present at position number 1. In this compound, there are 2 triple bonds present. Again, it is a butane and it is a butadiene. At position number 1 and position number 3, there are 2 triple bonds present. So that's why it is called 1,3-butadiene or buta-1,3-diene. You can write the name into both possible ways. Third part is this one, the name of compound. Now there is a triple bond as well as a double bond present. So the name of compound will be 1, 2 and 3. So name of the compound will be 1-butene 3-ine. We are dropping E of ene. Or you can write it as but-1-ene 3-ine. The next part was this one, where there are 2 triple bonds and a double bond. So we are going to number this compound from this side, that is 1, 2, 3, 4, 5, 6 and 7. There are 7 carbon atoms. At position number 5, there is a double bond which will be given the preference. So which will be given preference while naming it, not while numbering it. So it will be 5-heptene, position 1 and 3 are holding 2 triple bonds, so it will be diene. So heptene, dropping E of heptene and writing 1,3-diene. It can also be written as hept 5-ene 1,3-diene. The last part was this one. It is very simple one. The name of this compound is 3-hexyne or hex 3-wine can also be written. Now moving towards today's topics, that is relative stability of alkenes. There are 3 main factors that contribute towards stability of various kinds of alkenes. Relative means comparing stability of various kinds of alkenes. There are 3 main factors that contribute towards relative stability of alkenes. The first one is degree of substitution. How much substituted an alkene is. Do remember girls, highly substituted alkenes are usually more stable as compared to the alkenes which are less substituted. Highly substituted means when there are substitution like methyl or ethyl or propyl groups attached around a double bond. For example, we can have 3-4 different kinds of alkenes in front of us. This is a tetra-substituted alkene. You can see this is an alkene which is having 4 alkyl groups attached around it. This is a tri-substituted having 3 alkyl groups, bulky groups, and one of them is hydrogen. Then comes di-substituted having 2 alkyl groups and 2 hydrogens. Or it can be, alkyl groups can be on the opposite side or can be on the same side. And we can have mono-substituted in which there is only one bulky group. When we talk about their stability, we would say that tetra-substituted alkenes are usually most stable as compared to mono-substituted. Why it is so? Tetra-substituted alkenes, as you can see, the reactivity of alkenes is due to the double bond, the pi electronic cloud which is present above and below the 2 carbon atoms. When this is tetra-substituted, you can see the pi electronic cloud is in between center, and it is, this whole molecule is crowded with the alkyl groups, bulky alkyl group. So any electrophile which is in need of electrons, it would try to come near this one, but it won't be able to react or break the pi electronic cloud. So it will be more stable, it would be less reactive. As compared to this one, when alkyl groups are decreasing, there is quite a lot of probability for electrophile to come and attack this electronic cloud which is present above and below the carbon atoms. The next factor that contributes towards the relative stability of alkenes is stereochemistry or orientation. It is in fact related to isomerism as well, which will be discussed later on in detail in the next topics. Anyways, orientation or stereochemistry means when the alkyl groups are having bulky groups attached on the same side then it would be called a cis isomer. It is, for example, this is a butene. This is a double bond having two alkyl groups on the same side. This is called cis butene, and this is trans butene, in which alkyl groups are present on the opposite side. When we talk about among these two butenes, which one will be more stable one? We would say that trans alkenes are usually more stable as compared to cis butenes or cis isomers. Why it is so? The reason behind that is, in cis alkene, we can see the bulky groups are on the one side and pi electronic cloud is exposed from one of the sides, so any electrophile can come and attack this double bond very easily. But in case of trans butene, due to the repulsions, they are present far away from each other and still they are crowding the double bond, so that's why it will be more stable and less reactive. This is also due to the reduced steric interactions when R groups are on the opposite sides of the double bond. Steric interaction means there will be lesser repulsion between these two groups when they are present on the opposite sides as compared to this cis isomer. When these two are present on the same side, they would be repelling each other. That's why in that case, in case of cis butene, it will be less stable, and this structure trans butene is having lesser repulsions among various groups, so it will be more stable one. The third factor which contribute towards the relative stability of alkenes is conjugation of bonds. Now, what is meant by conjugation of bonds? There are three kinds of bonds that are being shown over here. We can have different dienes or trienes, etc., in which double bonds, 2 or 3 double bonds might be present in a chain. There can be three different types. There can be cumulated dienes or trienes, we can have conjugated dienes or trienes, we can have non-conjugated, or we can also call them isolated dienes or trienes. What is meant by conjugated diene? The conjugated dienes are those in which two double bonds are separated by a single bond. Non-conjugated or isolated dienes are those in which two double bonds are separated by more than one single bond. And cumulated dienes are those in which two double bonds are connected to the same carbon atom or similar atom. In these three types, among these three types, conjugated alkenes are usually more stable as compared to isolated or cumulated alkenes. For example, 1,3-butadiene is more stable than 1,4-butadiene. Such kind of questions are also given in the exam. You have to answer why 1,3-butadiene is more stable than 1,4-butadiene. The structure of 1,3-butadiene and 1,4-butadiene are being shown to you. You can see 1,3-butadiene and 1,4-butadiene. 1,3-butadiene is a conjugated system and 1,4-butadiene is a non-conjugated or isolated system. Details of why this happens will be discussed later on in the next few topics that are given in your book. But briefly, I can tell you over here that conjugated dienes are more stable than non-conjugated dienes, that is both isolated and cumulated, which is due to the factors such as delocalization of charge through resonance and hybridization energy. This is all due to positioning of the pi orbitals and ability for the overlap to occur to strengthen the single bond that is present between two of the double bonds. The single bond which is present between two of the double bonds will become more strong due to the pi overlap sidewise which is present near to it. So that's why its length will also become less as compared to the normal single bond length, and it will become more strong than a normal sigma bond. Now moving towards structure of alkenes. We have already studied about the structure of alkenes in detail in the first year when we studied about hybridization. Anyways, it is being discussed here again. This is an ethene molecule having double bond. You can see carbon is linked with two more carbon atoms, and pi electronic cloud above and below the molecule is shown, which can be shown in various possible ways. This is a sp2 because in ethene molecule or alkenes, carbon atoms which are holding double bond are sp2 hybridized. There are 3 sp2 hybridized orbital having angle of 120 degree among each other, and p orbital is left vacant or unhybridized. So this p orbital, these two p orbitals, sp2 are lying above and below, and this p orbital is lying above and below, sp2 are lying at angle of 120. This is the top view of the molecule, p orbital in the center, and these sp2 are present on the sides. This is one of the carbon atom which is sp2 hybridized. It is shown. Now when two of the same carbon atoms, when these are which are sp2 hybridized, when they are linked together, this kind of bonding will be done. sp2 and sp2 of two carbon atoms will join together. They will make up a sigma bond, and these unhybridized p orbitals will combine above. Their upper lobes and their lower lobes will combine together, and they will make up a pi bond. The bond length between two of the carbon atoms, that is sigma bond, is usually 1.55 Angstrom, but here it will be reduced to 1.34 because these p orbitals which are present above and below will bring two carbons more near to each other, and bond length will decrease and sigma bond will become more strong in that case. A good picture of ethene can be shown in this way as well, where ethene molecule you can see is holding two of the carbon atoms having two hydrogens attached at two carbon atoms, and pi electronic cloud is above and below. In between center there is a sp2 hybridized orbitals combining together to make up a sigma bond. Carbon hydrogen bonds are also having sigma bonds. Now moving towards preparation of alkenes. There are two important methods for the preparation of alkenes that are discussed in your books. The first one is dehydration of alcohols. Dehydration, the term D stands for removal, hydra for water. So the process of dehydration means removal of water from alcohols. How it will be done? As you can see, this is a simple alcohol which is being shown to you. OH is the functional group. Carbon atom which is attached with the functional group is called alpha carbon, and the carbon adjacent to alpha carbon is called beta carbon. Why they are shown over here? When water molecule is being removed from ethanol, this hydroxyl from alpha carbon and hydrogen from the beta carbon will be removed in the form of water, and double bond will be created between two of the carbon atoms. This will be done in the presence of concentrated sulfuric acid or upon heating as well. Simple process can be shown to you in this diagram, where aluminium oxide is being utilized as a catalyst. There can be various catalysts which will be utilized in this process: aluminium oxide, alumina, concentrated sulfuric acid, or P2O5. All these are dehydrating agents, so they can be utilized. There is a wool which is soaked in ethanol. It is kept on one side of the test tube. It is passed over heated aluminium oxide wire, and the vapors are collected above water in this test tube. These vapors are of ethene gas. This is the simplest way to prepare ethene from alcohols in the lab. Relative reactivity of various alcohols are: methanol will be least reactive, then primary alcohols will be more reactive, then secondary alcohols and tertiary alcohols will be highly reactive in that state. The simplest alcohol that we know is methanol. It is CH3OH. Primary alcohol is the one in which hydroxyl group is attached with the carbon atom, which is further attached with one more carbon. Secondary alcohol will be the one in which OH functional group is attached with the carbon, which is further attached with two more carbons. And in tertiary alcohol, OH group will be attached with the carbon atom, which will further be attached with three more carbon atoms. Conditions of the reaction are: various catalysts utilized in this reaction can be aluminium oxide, phosphorus pentaoxide, H2SO4, H3PO4. All of these are dehydrating agent that will help in removal of water. Temperature is usually kept between 340 to 450 degrees centigrade. Do remember, girls, these are called beta eliminations. As I told you, the hydrogen atom which is present at beta position will be removed along with OH to make water. That's why these reactions are called beta elimination reactions. Let's move on towards reactions now, how various kinds of alcohols are making alkenes. First come primary alcohols. Primary alcohol, as I have told you, hydroxyl group is attached with the carbon, which is further attached with one more carbon atom. When it is reacted in the presence of alumina and temperature is 340 to 450 degrees centigrade, hydroxyl from this carbon and hydrogen from this carbon will be removed and double bond will be generated between these two carbons, making alkene and water. Now moving towards secondary alcohols. Secondary alcohol, I have told you, is the one in which hydroxyl group is attached with a carbon, further attached with two more carbons. It will react with 75% sulfuric acid under a lower temperature now, that is 140 to 170, and it will make an alkene. Hydroxyl will be removed from this side and hydrogen will be removed from this side, that is beta hydrogen, and water molecule is formed. So double bond is created on this side. Tertiary alcohols will react very fast and under very less harsh conditions, I would say. Tertiary alcohol is the one having hydroxyl group attached with a carbon, which is further attached with 3 more carbons. Here it is reacting only in the presence of 20% sulfuric acid and temperature range is 140 to 170. We can see alkene, hydroxyl group will be removed from here, and hydrogen will be removed from this side, and this alkene will be produced along with water. Next method for the preparation of alkenes is dehydrohalogenation of alkyl halide. Now the term D stands for removal, hydro for removal of hydrogen, and halogen for the halogen. So removal of hydrogen and halogen from alkyl halide is called dehydrohalogenation. Removal of HX, that is hydrogen halide, from alkyl halide is called dehydrohalogenation. Simple method is being shown over here. This is an alkyl halide having halogen attached at any of the carbon atom. It will react in the presence of alcoholic KOH. This is alcohol and this is KOH. Alcoholic KOH will do the same. It will help in the removal of halogen as well as hydrogen from the molecule, and double bond will be created between these two molecules. Halogen will be removed and hydrogen will also be removed. This halogen will be picked up by the potassium ions and it will be converted into potassium halide, and this hydrogen will be picked up by the hydroxyl ion and it will be converted into water. Conditions for this reaction are: catalyst required is alcoholic KOH, and again this is a beta elimination. This carbon is alpha carbon and this carbon is beta carbon, so hydrogen from the beta position is usually eliminated in this reaction as well. Some more examples of dehydrohalogenation of alkyl halides can be shown. Typical example is a bromoethane. Bromoethane, when it is reacted in the presence of KOH and a little bit heating, ethene molecule is produced. Along with that, KBr and water is produced. These hydrogen bromide is usually detached from the major carbon chain, and potassium picks up bromine and hydroxyl is picked up by the hydrogen, making KBr and water. Again, you can see alpha and beta carbons are mentioned. Another example is 1-chloropropane. When halogen is attached at position number 1, then this halogen will be picked up by potassium, making KCl, and hydroxyl will be picking up beta hydrogen and it will be converted to water. In case of 2-chloropropane, where chlorine is attached at position number 2, now there can be 2 beta hydrogens available. This carbon is also beta carbon, this carbon is also beta carbon. So hydrogens attached with beta carbon will be beta hydrogens. So these 3 and these 3 hydrogens are beta hydrogen. Now any 2 of the hydrogens from any side can be removed because this is a symmetrical molecule, and double bond will be created over here, and along with that KCl is produced and water is produced. That is all about preparation of alkenes. Now moving on towards reactivity of alkenes. Alkenes, as we know, are very reactive compounds as compared to alkanes. Alkanes were paraffins, they were not very reactive. The reason for the reactivity of alkenes is it is easier to break pi bond and the sigma bond will remain intact, and sigma bond has become more strong now because pi electronic cloud is present above and below the carbon atoms, which can be attacked very easily by the electrophiles. Electronic density of pi bond attracts the electrophile towards itself, so making reaction easy. and one pi bond, when it is broken up, it results in the formation of two sigma bonds. Two new bonds are usually made in this way. So there are various reactions, many reactions are given in your book. Today we are discussing only two of the reactions. First one is hydrogenation. The term hydrogenation means addition of hydrogen to the double bond making a saturated compound. This is called hydrogenation. Simple hydrogenation is shown over here. Double bond will be, one of the pi bond will be broken up only, and hydrogen, this bond between hydrogen atoms will also be broken up, and both hydrogens will be added up with the two carbon atoms holding a double bond. This happens in the presence of nickel as a catalyst, and temperature is usually 150 to 150 degrees centigrade. The molecule produced will be simple ethane now. Conditions for this reaction are, we can utilize palladium or platinum metal at room temperature, or we can use Raney nickel as well. This Raney nickel is very important, and usually it is utilized in the normal routine. Temperature is usually, moderate temperature is required, and moderate pressure, that is 1 atmosphere, is required in this process. Now what is this Raney nickel? This is very important. Raney nickel is also called spongy nickel, and it is very finely grounded or finely powdered solid kind of nickel. It is usually derived from nickel and aluminium alloy. This is the Raney nickel. It was developed in 1926 by American engineer Murray Raney for the hydrogenation of vegetable oils. That's why after his name this nickel is called as Raney nickel. It can be prepared in the lab by treating nickel and aluminium alloy with caustic soda by this reaction. Nickel aluminium alloy is reacted with the caustic soda or sodium hydroxide in the presence of water, producing nickel in the finely grounded state. Along with that, sodium aluminate and hydrogen gas will be released in the process. This Raney nickel is very important in hydrogenation. It is usually utilized even in industries for hydrogenation of vegetable oils as well. Some more examples of hydrogenation can also be shown. Any kind of double bond can be taken. It will react in the presence of hydrogen and Raney nickel, and double bond, pi bond will be broken up, creating hydrogen bonds between carbon and hydrogen, converting it into a alkane. Similarly, you can take even benzene and react it in the presence of nickel catalyst. There are 3 double bonds, and all of the pi bonds will be broken up, and hydrogens will be added at their place, converting it into a simple cyclohexane. This reaction is very important reaction. The next reaction is hydrohalogenation. The term hydrohalogenation means addition of hydrogen and halogen to the double bond making alkyl halide or haloalkane. Do remember, this is opposite to what you have studied in the preparation of alkenes. We studied about dehydrohalogenation, that was removal of hydrogen and halogen from alkyl halide. Now this process is totally opposite to that. This is hydrohalogenation, means it is addition of hydrogen and halogen to alkene molecule. There are two kinds of this reaction, hydrohalogenation, which depends upon the type of alkene which you are using. The first is symmetrical alkenes. If we are having symmetrical alkenes, then reaction will proceed in a normal manner. If there is a double bond present, this is a symmetrical alkene or ethene being shown to you. It is when hydrogen and halide, they are added to alkene. Double bond, pi bond will be broken up. Hydrogen can be added to one carbon and chlorine can be added to other carbon, and ethyl chloride will be produced. This is a symmetrical alkene. Symmetrical alkene is the one which is having same kind of environment around the double bond. This is another. 2-butene is also a symmetrical alkene. You can see around the double bond environment or attachments are the same. So HCl can be added up and it will be broken up. Hydrogen can be added up with this carbon and chlorine can be added up with this carbon. Even otherwise, if you do otherwise, hydrogen is added here and chlorine is added upon this carbon, even then the product produced will be the same. That will be 2-chlorobutane. Order of reactivity of various halogen acids that are reacting here in this reaction is: hydrogen iodide will be reacting very fast, hydrogen bromide will react at a moderate rate, and HCl will be reacting at a very slow speed. So hydrogen iodide will be most reactive in this case. This was the case when we were having a symmetrical alkene. Mechanism of the reaction can be shown in this way. This is a double bond which is shown with the green line, and two carbon atoms are holding these two. These are the two electrons between two carbon atoms. When HCl is making a bond, the hydrolytic breakage will be done. Chlorine, being more electronegative, will take this whole electronic pair towards itself, and it will be changed into chloride radical, and hydrogen will be left behind with no electrons. So what will happen? The double bond, the electrons of the double bond will be donated to hydrogen, and hydrogen will get attached over here with this carbon atom. The other carbon now will be electron deficient, and it will have a positive charge. In the second part, chloride radical will attack this positive part, or the positive carbon, and chlorine will be attached over here with this negative charge, and a bond will be made. So this is a haloalkane or alkyl halide that is produced. First one is the electrophilic attack. You can see electrophile, electron loving species, that is proton, was attached with the carbon atom which was holding double bond. And the second part is the nucleophilic trapping. This is a nucleophile which is in search of nucleus, which is in search of positive charge, that is being provided to it by the carbon atom. So chlorine will be attached in this way. The reaction mechanism that is shown in your book is this one. It is again the same. The proton or hydrogen, which is partially positively charged, will be attached with the carbon atom, and it will be having a positive charge because it is attached with the carbon atom. Now the other carbon will be rendered positively charged, which will be attacked by the halogen, and this is how a haloalkane would be produced. This was the mechanism for symmetrical alkenes. Now moving on to the next case, where unsymmetrical alkenes can also undergo hydrohalogenation. If this is the unsymmetrical alkene which is being shown, why this is unsymmetrical alkene? Because we can see around double bond, the environment is different. This double bond is having carbon atom which is attached with one of the hydrogen and one methyl group, but this carbon is attached with two hydrogen atoms. So now there are two possibilities if we add hydrogen chloride in this molecule. The first possibility is when the double bond is broken, hydrogen can be added up with a middle carbon and chlorine can be added up with a terminal carbon, making 1-chloropropane. Another possibility is hydrogen can be added with the first carbon, and chlorine can be added with the second carbon, making 2-chloropropane. So out of these two, which product will be produced? Among these two, the first product is not produced, but the second product is the major product, and this is the product that is produced. This hydrogen is attached with the terminal carbon atom and chlorine is attached with the middle carbon atom. Why it happens? Why this hydrogen is attached with the terminal carbon atom only? Why it cannot be attached with the middle carbon atom? This is due to a very important topic in this alkenes, that is Markovnikov's rule. Markovnikov defined a rule for unsymmetrical alkenes, and he told that when unsymmetrical reagent adds to unsymmetrical alkene, the negative part of the reagent gets attached to that carbon atom which is jointed to the lesser number of hydrogen atoms. You can see this is a asymmetrical or unsymmetrical alkene. The one that I've shown you just now, this carbon is having two hydrogens and this carbon is having methyl group and a hydrogen. This is also an asymmetrical or unsymmetrical reagent that is being added. Now he told that negative part of the reagent, bromine is the negative part, it will get attached to the carbon atom which is jointed to lesser number of hydrogen atoms. So this carbon is having more hydrogens, that is 2 hydrogen, but this carbon is attached only to the 1 hydrogen. So bromine will be attached with the carbon atom that is holding lesser hydrogen. In other words, we can say that First product will be the correct product that is produced in which bromine is attached with the second carbon atom, and this product will not be produced in which bromine is shown to be attached with the first carbon atom. In simple words or routine words, we can say that rich gets richer. Carbon atom which is rich in the hydrogens will receive more hydrogens, and it will become more rich in the number of hydrogen atoms. Now I am going to show you some more examples which are following the Markovnikov's rule. You can see in this example, this is a double bond, and this carbon atom is having 2 hydrogens and this carbon atom is having 1 hydrogen only. When HCl is added to it, chlorine, according to Markovnikov's rule, should go towards the carbon atom holding less hydrogen, and hydrogen that is shown in the red color will be attached over here with the terminal carbon, and it will make it more rich in the number of hydrogen atoms. So this will be the major product produced. Other possibility is where chlorine can be attached with the terminal carbon and hydrogen attached with the middle carbon is the minor possibility, or minor product will be produced in this case. Some more examples can be shown where you can see there is terminal carbon atom holding 2 hydrogens, and this is the carbon having 1 hydrogen only. When HCl is added, chlorine is being attached with the carbon atom having less hydrogens, and hydrogen is attached with the carbon atoms having more hydrogen. Same can be shown, another example is being shown where there is a methyl attachment along with the double bond. In this case, this carbon is having 2 hydrogens, but this carbon is having no hydrogen at all. It is having only methyl group attached. So chlorine gas will be attached over here, chlorine radical will be attached here with this carbon atom which is having lesser hydrogen or no hydrogen, and hydrogens will be attached with the carbon already having more hydrogen. Other possibility is the minor product produced. In this reaction, again there is a methyl group attached here along with a double bond. So this carbon will be having 2 hydrogens and this carbon will be having no hydrogen at all. So chlorine should be attached with this carbon atom and hydrogen will be attached with the second carbon atom in this case. I hope Markovnikov's rule is now clear to you people. It is a very important topic. That's all for today, girls. I hope you have understood everything. If you have any queries, any questions, you can ask me in the WhatsApp group. That's all for today. Thank you very much. Have a good day.